meeting. And yeah, and then we will begin. So our class called Tachyon Technologia, and basically tachyon is just a particle that moves faster than light that scientists believe that it doesn't exist. And technologia is the ancient Greek word for technology. But we will not just talk about technology. We will talk about history of science and asteroid determination for our first part. And for the second part, we will talk about string theory. For the third part, we will talk about the superluminal motion and deep space exoplanets. And for the final part, we'll talk about postmodernism literature. So I'm going to start to talk about the first part. So I tried to share full screen last time, but it doesn't work. So I hope like this is fine. This first part is about history of science and asteroid orbital determination. So first, it's just the person Copernicus that everyone knows well. We know that he is a Polish priest and scientist. We know that he educated at the University of Krakow. He wrote on the revolutions of heavenly spheres in 1543. He was commissioned to find astronomical justification that the papacy could change the calendar so that they could correctly calculate the date of Easter. And Copernicus' work provided an intellectual springboard from which the scientists could pursue questions about the Earth's position and universe. And so like what so then we would briefly talk about the Ptolemaic system. So Ptolemy, a Roman citizen of Greek ancestry, wrote the Agmax was considered the authority on the astronomy throughout the Mid Ages, and it suggests a geocentric model of the universe, and something that probably everyone knows well. The Copernicus universe is its model adopted many elements in the Ptolemaic model, but transfers them to a heliocentric model, which assumes that the Earth moved about the sun in a circle. And he also proposed that the farther planets are far away from the sun, the longer they took to solve around it, which enabled astronomers to rank the planet in terms of distance from the sun. And also, like, although very few astronomers embraced Copernican systems, at least for a century, it did allow other people who were not satisfied with Ptolemaic view to think in new directions. However, the model was no more accurate than Ptolemaic model in predicting planetary positions because it still used perfect circles. And then it comes to Bragg. So Bragg compiles a very accurate naked eye measurements. So Bragg's contribution to the science is that he did not believe that Copernicus' view and spent much of his life advocating for a geocentric system. He possessed that Mercury and Venus revolved around the sun, but the moon, the sun, and other planets revolved around the Earth. He collected very detailed data of his observations and countless contributions. Now we will talk about the person. So his contribution is that he studied under Bragg and was given to the data when he died. Kepler, unlike Bragg, was a convinced Copernican who found a mathematical proof of a sound standard universe. He found that in order for heliocentrism to be true, planets must have an elliptical rather than circular path. And he has published his findings in a book called The New Astronomy, in which he used Copernicus' sound standard model and Bragg empirical data to solve the problem of the planetary system. So his observation, his discrepancy has been only like 8 arc minutes, which lead him eventually to ellipses, which is really accurate. And he has said that if I had believed that we could ignore this 8 minutes of arc, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore, those 8 minutes pointed the road to a complete reformation of astronomy. So then it's about Kepler's first law. So many people also probably know that already. So the orbit of each planet around the sun is ellipse with the sun at one focus. And so semi-major axis is half of the distance between perihelion and aphelion, which we'll talk about that again later. And also the eccentricity is also important to know in this picture. And I think a lot of people also know about that. And the Kepler's second law is that as planet moves around its orbit, it sweeps out equal areas in equal times, which it means that a planet travels faster when it's near to the sun and slower when it's further from the sun. And we have the third law that more distant planets orbit the sun at slow average speeds, obeying the relationship the square of the period equals to the third power of the average distance from the sun in AU, so the semi-major axis here, and it's in astronomical units, which is AU, so that they can take the equal sign instead of just proportion to. So what determines the strength of gravity? Also, you probably know that about already. So every mass attracts to the other mass. Attraction is directly proportional to the product of their mass, and attraction is inversely proportional. How does Newton's law of gravity extended Kepler's law? Kepler's first two laws apply to all orbiting objects, but not just planets. So ellipses are not only orbital passes, but orbits can also be ellipse, like unbound. It can be like parabola or hyperbola. So parabola has eccentricity equals to 1, and hyperbola has the eccentricity larger than 1. And then it's the Newton's version of Kepler's third law, and P is period, A is semi-major axis, and 1 plus m2 is the sum of the mass of the planet and the sun, so sum of the object masses. Newton has generalized Kepler's third law, so Newton's version of Kepler's third law is that if a small object orbits a larger one, and you measure the orbiting objects or its orbital period and average orbital distance, then you can calculate the mass of the larger objects. And here's some examples of like doing so. Then now I will talk about the 6 orbital elements. The 6 orbital elements is what defines the path of the asteroid, the path of planet. So the first is semi-major axis, and the range doesn't have a range. You know, like it can be the planet or the asteroid can be like very far away from the sun. It has a like really long orbit path, but it can also have a really small one, so it doesn't really matter. And eccentricity, we know that the eccentricity for ellipse is between 0 and 1, and if it's 1, that's parabola, and larger than 1, that's hyperbola. Inclination, which I'll introduce later with graphs, it ranges from 0 to 108 degrees. And latitude of ascending node, I'll also introduce later. So its range is from 0 to 118, and also we have argument perihelion and Anomaly from 0 to 360, because they simply just describe the things in a horizontal view on that plan. So and on that plan it have like all around, so it's like 360 degree. For inclination, and longitude sounding node, they are like the relative relationship between two play like two surface, so that you don't really need to have like 316, so it's just like above 118. So that's what about it. I need to check the chat box. Yeah, I will try to sign this presentation after this meeting. And also, I was send a record, which I think I will put that in the class page. And then we go to our next slide. The next slide is about those elements. So basically, the longitude of a ascending node, we can see it is here. It's the angle from vernal equinox to the ascending node. And we have the argument of perihelion, which is the angle between the ascending node to perihelion. So perihelion is a vector from the Sun to the perihelion of the planet of the asteroid. So that's perihelion. That's like this is perihelion's point, but this vector is also called perihelion. What diagram is that? This is a diagram of like here is the sun and here is the planet, or like the planet can also be asteroid at the same time. So, and this is like the plan, the elliptic plan, and this is like the plan of the planet and the sun, and we are like expanding the element here. Also, like we have the true anomaly. So true anomaly is that when we have like this like 5 of the element, we can determine the path. But true anomaly tell you where exactly the planet or the asteroid is on the path. So like the planet can be here, the true anomaly is this. So the planet can be here, the true anomaly is this angle. Planet can be here, the true anomaly is this angle. And then we will go to the next slide to introduce about semi-major axis. So it is well known that the celestial orbits has elliptical orbit around the sun. So with the sun at one focus of the ellipse on the semi-major axis, A is the average of the asteroid's distance from the sun at its perigee and apogee. So perigee and apogee is also like perihelion, aphelion, but that's like specifically for the sun. And then eccentricity. Eccentricity of the orbital ellipse is a numerical measure of how scratched the elliptical orbit is. A perfect circular orbit has E equals to 0. The ellipse has E between 0 and 1, and the parabola has E equals to 1. The hyperbola has E larger than 1. A larger eccentricity implies a larger ratio between the distance to the aphelion and the distance to the perihelion of the asteroid. So for the orbital determination of the asteroid, like we'll work with elliptical orbit because like asteroids just travels around the sun. It's not in a perfect circle. So in this case, the eccentricity equals to C over A, and C is the distance from the center of the orbital ellipsis of the asteroid to the sun, and A is the semi-major axis that we have mentioned before. And then it's the inclination. So the orbital ellipse of an asteroid and the orbital ellipse of the Earth's revolution lie on two plane. So like this is the Earth and Sun. The Sun is here, and we will have a Sun asteroid like this, and it has an angle. So like this is Earth, Sun, and asteroid Sun. So the angle here is called inclination. It's the inclination angle I. And so like the I ranges from 0 to 180, where the angle from 0 to 90 indicates east to west motion, while the angle from 90 to 180 indicate retrograde motion, so which is east to west motion. And then it's longitude of ascending node. So longitude of ascending node, omega, is if the inclination doesn't equal to 0, then there are 2 points where the orbit of the ellipse intersects with elliptical plane. At the ascending node, the asteroid changes from being below the ecliptic to be above the ecliptic, with the top section of the plane is the one which contains Polaris. So the longitude of ascending node is the right ascension of this point. And another way of thinking about longitude of ascending node is that this is the angle between the vernal equinox and the line of nodes. And also argument of perihelion. So the angle of argument of perihelion is measured from the ascending node to the position of the asteroid when it's at perihelion, with the center of that angle between these 2 points being the location of the sun. So this angle ranges between 0 and 180. And we also have the mean anomaly. So mean anomaly is not changing over time, and true anomaly is changing over time. So true anomaly is changing over time because it determines the current position of the asteroid and the position of the asteroid from the perihelion. Perihelion is 0. Since the angle ever goes counterclockwise, so it ranges from 0 to 360. And then so how to determine an asteroid? So the position, so the process is like this. First, we take images with a telescope, and we need to take at least 3 sets of image because we know that with 3 points, we can determine a ellipse. Also 3 points can determine a circle. But 2 points is not for determining circle, but ellipse needs 3. And then for each 3 sets of data, you need to take 3 sets of data again. 2 sets are enough, but it's better if you take 3. And because how to find the asteroid is that now you need to use the data reduction software such as AstroImage-J. So first you need to do the reduction to just subtract the dark current, subtract the hot pixels, subtract those flux in the cameras so that you will have a clean picture. And the second is that because the asteroid is just so close to us, but all the background stars are really, really far away from us, like 4.2 thousand of solar and 2 million light year for the next closest star. So it's just so far away from us. And as a result, they don't really move compared to the asteroid. So if we set all the stars as the background, the things that move just move a bit, move in a straight line in 3 pictures. That's our asteroid. How do we find that? We just because our Earth revolves itself, so the sky background won't move, but we need to align them together. So some stars form certain pattern, like a pattern of the pattern of a crack mark line, the pattern of a flower, and you just choose them in each picture and you just align them, then they will be overlap together, and so the asteroid will move. Why the asteroid move in a straight line? Because since it's moving elliptic shape, however, it's just so far away from us. I don't know, it's not so far away from us. Sorry, it's because we just took that from a so short amount of time. So it was short amount of time. So also it's relatively far from us, although not as far as the stars. The stars are much further. What you see is that a segment, which is a line. And also you can take if you don't blink through image, you can also take an image of longer time, and there's something like a white line, that's the asteroid because it moves. And then we have the relative stars, and the stars has a corresponding pixel. The asteroid has its corresponding pixel, and the pixel number is related to its magnitude, or the magnitude is the brightness. So like if it's bright, then you have more pixel on your camera, and you can compare to the magnitude of the background star in the software such as SIO DS9, and because you have the number of the magnitude of the stars, you have the pixel of the cell, you have the pixel of the stars, you have the pixel of the asteroid, so you can get the magnitude of your asteroid. After you get the magnitude of your asteroid, you can also determine its shape approximately, because shape is related to distance, and also like magnitude is related to distance and the shape. So with magnitude and distance, you can get the shape. And also on the picture, because we have all the previous data, all the relative position of the stars, so you can also get to know the right ascension and declination of the asteroid. And the right ascension declination, we can use that because that in Python we can guess the distance between the Earth and the asteroid, and we can like calculate also calculations, and at the end we can guess the speed of the asteroid, and also the speed on the like the speed of the asteroid in different way, and also like the acceleration of the asteroid. So after getting them, we can just do all sorts of calculations to calculate the 6 orbital elements. And after we have the 6 orbital elements, we can just plug them and we can stimulate them like this. But also we don't really need to stimulate that if it's not for fun. It's just knowing that scientifically 6 orbital elements just determine what the asteroid is. So that's enough. And yeah, so like for like when we try to guess the vector, the distance should be guessed with scalar equation of Lagrange, and it's just a approximating work instead of just deduction directly. That it's through the iterations that we finally get the results. So definitely, like we said, the result need to be as close as 10 to the negative 14th power, and then we will confirm that it's close enough. We will have precise data enough, and we are good to go. So this is the first part of the history of science, and also asteroid orbital determination. If you have any question, please ask in the chat. And also, like after this, we will have a brief discussion after like this and the next class. But also feel free to send those thinkings on everything, comments and questions in the chat all the time. So the second part is briefly about string theory, but just super briefly about that. So we know that general relativity and quantum mechanics cannot be unified, and so that but people are trying to just find the unification law all the time. And the major problem is that gravity cannot be integrated to it. That's why like unification law keeps fail. But for the other three forces, the electric force, the electromagnetic force, strong force, and weak force, they have all like unified. So first is that the electric force and magnetic force has been unified really early to be the electromagnetic force. That's the first step. The second step is that people consider that if the universe become really hot, if we go back in time, then the electromagnetic force and the weak force can be unified to what called electric weak. And Then if you rewind the tape of the evolution of the universe far back, and then people get that the electric weak and the strong force can be unified to be standard model. However, the gravity had not been integrated. Then that's why quantum mechanics and general relativity came in, but they are still incompatible. So for quantum mechanics, briefly about it is that it's just a so turbulent world. In that world, red and green light can be on at the same time. You can go through one way and the other at the same time. You can go back in time, and the like a bottle of water in your hands don't really need to be like this is orange juice is orange, but it can be like red, blue, and anything. So it's just a really uncertain and turbulent world, and you can go through a wall if you want in this world. The second is about then we will briefly talk about string theory. So before like people think that all the particles are point-like. However, people think that it might be a string and it's like vibrating, it's just so tiny, it's vibrating like a violin string. And then that's the birth of the string theory. So this person, um, this person first found a reading about of like biology, which is a reading like 300 years ago. So he found he was also like trying to um, have some work to do with the strong force and electromagnetic force, and but that doesn't really like make the string theory become famous or caught a lot of attention. Linda Susskind is a person who just found that does that equation just portray a string-like property of the particle. So he just takes some study on that. However, it has a lot of problem at the time. So the problem is that it needs a tachyon. So tachyon, we have mentioned in the start of the class that tachyon is a particle that moves faster than light. It transports information faster than light, which scientists have believed that it's just impossible for such a long time and even today. And second is that it needs 10 dimensions, so they don't really understand why. And the third is that it requires a massless particle, and also it has assortment of anomalies, which means that on the two sides of the equation, which it should be equal, but you get different answers. You know, one like 100, another is like 500 on the equal sign. So that's like assortment of anomalies. So then, so like the history of string theory is that like at the time, so like there's something still missing in the standard model, and then Michael Green joined this research on the string theory, and they tried to solve the assortment of anomalies, which in the summer of 1994, on a like thundering day, they just find that on both sides of the equation they get 496, which is the same. So they solve the problem, and also they still have like the massless particle, but people have seen that graviton, the particle that has gravity, might be somewhat is the massless particle. So that's like about that. So how does people like so people are trying to find that. Now we'll talk about that later. And so what also like topology is important for string theory, but no, I'm not elaborate here. So based on topology, we know that it's like since wrap or tail is the same. So but like with topology, it has the idea that the higher dimension can change the world. So if we have like elements you have a 10th dimension, 11th dimension, you can have the wormhole. However, like the problem is that now people are looking forward for one unification theory, but now people get 5 string theories, which just not unified together. It's just not a good idea. So in 1995, this really smart guy, Edward Witten, just he introduced the M theory, which unifies the 5 string theory, which he believes that the 5 on string is just like 5% in the middle, but it's one person. That's one person's projections. So you unify them, and people are like so confused with like why this is M theory. Some people say it's like mystery, magic, matrix, mother, monster, outside down W for Witten. But Witten himself says that it stands for murky, which our understanding about string theory is just so murky. And yeah, so another part is that if M like for M theory, he also like changed it's a string-like particle to it's a membrane-like particle. And so what's the people's belief is that probably we have the parallel universe, probably we're just left in one was the bread, one was the membrane. And why we cannot know like about the other dimensions is probably the other dimension is just in another loaf of bread. It's close to us, but we can never reach. So actually, string theory's idea of dimension is that we only have one dimension of time, and all the other dimension is space. But also like there's some like postulation of dimension, which people think that this time should also increase in 1 dimension, 2 dimension, 3 dimension, 4 dimension like this. So there's like this difference, and how people can have higher dimension, just that it gives a larger degree of freedoms. It's just curved up dimension. It's like if you see a column, like a not really large column but small column, and you see an ant, you saw that the ants can only go upward and downward. However, the ants can just go around the column like this. So if you see from far away, you can see that you saw it's only like 1 dimension, upward and downward, but in fact it's cut off, so it can go a lot. And people think that probably the other like 6 dimension or like after M series 11 dimensions, the other 7th dimension just curved up in some way that we can't see them. So so people was this people think that what gravity, we know gravity is much weak than the electromagnetic force. So people they think that probably like on a loaf of bread, the graviton is just like the sound. It can just fall down. It's just like sugar, but the electromagnetic force is actually stick on the loaf of bread, so it's much stronger. The gravity can just fly to the higher dimension. So yeah, so they believe that the graviton are just a loop like this. So it's not bound on the surface. It can just blow around. But they believe that the electromagnetic force is like this string just has its 2 ends tied on the plane of our dimension, so it cannot like flew away, so it's so strong. But we don't know about that. So people trying to test that out, they just use like third formula before and then third, they just make that 2 particle travel at nearly the light speed, so they will crash. And if the crash just reduce the weight of the total mass, then probably the reduced weight is a graviton just move to the higher dimension. But people don't know that. So that's about string theory. So string theory bring us like all those possibilities, but at the same time it can be totally wrong. But it's based on mathematical inference. It's based on mathematical deduction. So even it is wrong, people still like leave something like Newton's law is not like completely right, but Newton's law is still widely adopted and used, and all those techniques and technology and thinking that has been adopted when approaching to this problem, which might be run, will be helpful in developing the further thinking. And some people like have question about like why it has higher dimension in the loss clause. Is that something that we have actually have some discovery about? It's not. So basically, it's just the result of mass. So like to make that equation, to make those things valid mathematically, we need higher dimension to achieve that. So um, so yeah. So what do you think are the most fantastic part or fascinating part of the string theory? What do you think, like how to lead and science discovery? Is that like think about the example of like Kepler, think the example about like here Leonard II. What do you think that is a way that people like actually promote new ideas? And also what do you think is like the relationship between history and science? Do you have any questions? Just feel free to ask them.
How many dimensions are there?
So like for the string theory, people believe that there's 10 dimension, and for the M theory, people believe there's 11 dimension. However, we don't really know like how exactly the world has like because all those are calculated mathematically. So our current world is like 4 dimension of space-time, 3 dimension of space plus 1 dimension of time. For the 11 dimension, people believe it's like 1 dimension of time and all the other space, but people have different interpretation to the dimension. And yeah, that's like if also like for 10 dimension, people believe that's 1 dimension of time and 10 dimension of space. But why it result like that is mathematically in the real world we have no idea, no certain idea. And also like some theory has lead to like 26 dimension or like infinite number of dimension, but that's just mathematically. So I will go to the next, and just feel free to set any questions in the chat and send any comment in the chat. So this is about superluminal motion and about the exoplanet in deep space. We will talk about the theoretical method for detecting exoplanets in deep space. So superluminal motion, it's not similar to Tachyon. It's something that is actually exists. It's something that actually it's perfectly like for the scientific theory. It's not just something that we can't prove to be true. We never know if it's true or not. And superluminal motion is more like illusionary or like geometric phenomenon, but we can really like see the things travel faster than light. At least see that the information is not travel faster than light with superluminal motion. So basically, the keywords for this I need to clear my Discord and Slack, which is so annoying. So like the keyword for this part is exoplanets, Microlensing events, superluminal motion, and also we will briefly mention about machine learning, and also we will mention about the calculation of cosmological distance. So in 1995, Pegasi 51, the first exoplanet, was confirmed and is found and confirmed. And actually, the very first is the one that found in 1989. However, that one's not confirmed, and that one has really like rough data, and also that one has a whole star, which is just basically that it's a pulsar. And in 1990, in 2019, Nobel Physics Prize was given to the astrophysicist who found Pegasi 51b, which are Mayer and Quilos. And until October the 22nd this year, 4,296 exoplanets were found and confirmed. However, all the exoplanets that we have found currently are just within a small area within the area of 300 light year. What is exoplanet? Good question. So exoplanet is a planet beyond the solar system. So like it's called like extrasolar planet if you want to talk about it in detail. So also a planet that's not like the eighth planet in the solar system that we know about, but it's a planet like in the Milky Way or beyond Milky Way are all counted as exoplanet. They have like different host star. They have host star that is not the sun, but any other like star is exoplanet. And so would human be able to live on exoplanet? Possibly, but not now because just like I have mentioned in the asteroid part, all the stars is just so far away from us. Like the most close to us is millions of light years, so it's just far away. But still, we will discuss about its habitability, because why we want to discuss about habitability is that like even we can live on that. Possibly there's some creature life on that, and it would be great to see the evolution of those life. And yeah, so currently all the exoplanets that have been discovered is within 300 light year, and it's not able to detect any exoplanet beyond the Milky Way singularly yet, but we will introduce some methods that can lead to that possibly here. And the age of our Earth is 4.5 billion years, and the age of the universe is 140 billion years. So the Earth can be counted as early exoplanets. And when we observe the early exoplanet or the exoplanet in deep space, because it's deep, so actually we're seeing the past, we are just like, we can see the birth of the Earth, possibly, which would be really cool. And the problem is that we can use microlensing events to discover the exoplanet in the Milky Way. But if we want to discover that just beyond the Milky Way to a really far place, then it would take a long time. It would take like 15 years. So in order to reduce that to about 10 days, we need the superluminal motion to be a source of the microlensing events in order to accelerate the event. And also because we have just need to search a lot of um, um, a lot of time, a lot of space, so we will need auto recognition to recognize those microlensing events. Otherwise doing that humanly is just too much. It's not really possible. Sorry that I can't catch cold a lot a bit. And then it's about recent progress of exoplanet detection. So the data here is to the October the 22nd. So 4,296 exoplanet has been confirmed. Among them, 1,461 are Neptune-like, just like the Neptune. So it's easy to understand. 1,343 are gas giants, which are similar to Jupiter. and Jupiter is a gas giant, and with 1,383 are super Earths. So super Earth is terrestrial, but super Earth is much massive, much larger than the Earth. Then it's terrestrial. So terrestrial is basically just like the Earth, of the same size, and is also a rocky planet. And the sixth hasn't been classified. And the most important mission for detecting exoplanets, the first is Kepler and K2. K2 is just a successor of Kepler that has confirmed 2,814 exoplanets, and for the test, which is called transient exoplanets um, satellites satellite survey satellite. It has confirmed 81 exoplanet, and both of them are really important. And also on the ground, they have like both of them are sent into the sky, but on the ground they have WM Kirk, which is also important. WM Kirk are just two telescopes in Hawaii with the mirror, which is as the lens, which is as large as 10 meters. Then it's about the habitability of the exoplanets. So liquid water is important, at least for carbon-based creature. And the host star type is important because we need liquid water, and also host star type determine whether it will have long presence of liquid water stability of the planet system. Because if it's super hot type of host star, it will just burn out so quickly, and after it burns out, like if the sun burns out, it will become red giant and it will overheat the earth. So the life on the earth will go on with that, and so the life has a time to develop to evolve. So we need the stability of the system. We need to have enough time for the life to just evolve, and also the distance between the star and the planet. Like it's also because of the temperature. Like it's too hot, that's too cold, and just right. And the planet size should be about 1 to 2 um, times of the Earth, because it determines the thickness atmosphere. If it's so large, it have so thick atmosphere, then the light cannot go through. And if it's just have too thin atmosphere, then it will have a very, very dramatic temperature, or like so that it generally suits for the life. And also the composition of the planet. Terrestrial is what people think is important for the carbon-based creature. If it's not carbon-based, possibly like helium-based, hydrogen-based, if that's the case, it would be so different. But some people believe that if it's this creature, there should be carbon-based, and some people has actually speak about that. Probably it doesn't need to be like so far away in the habitable zone. It can be close to the sun, which but those planets should be tidally locked, which means that it has like one face, always facing the sun. Like just like the moon, when it faces the Earth, it always has one side. So that's like the planet always face one side to the sun, and as the dividing line of the hot side and the cold side, it can be like warm side, which can be habitable, but some also argue it's not impossible, it's like just impossible. And also people has argued that because it has wind on that planet, so even it's not out the dividing line, but an area out the dividing line, it can be like having like appropriate temperature because it has wind to just move the hot air and the cold air around. And then this part is about the generality and speciality of the exoplanet. So for the x-axis for the first picture, it's the orbital period. The y-axis is the orbital eccentricity. And this red point are the planet in the solar system. So we can see the planet in the solar system have a relatively low eccentricity. So the low, also like it's about 0.2, or like it's for the largest and for the other are all about zero point 0.1. However, the eccentricity of the exoplanet is just so diverse, and the average eccentricity of all the exoplanets are actually much higher than the average eccentricity of the planets in the solar system. And the second is that the orbital period and the orbital mass relationship, that from this we can see that a lot of exoplanets, they have really small period and really large mass. However, it probably should not be like the overall trend. It can be a lot exoplanet here also, but if it's just not close to the sun, which means it have like dimmer light, which means that it take a long time to go through the sun for winds, and which means that if it doesn't have a high mass, means that it's so small, low brightness, it's just so hard to detect with current technology. So we have a lot of planet here, probably just because of our technology instead of our general trends. And that is for method of detecting exoplanet. So we have got all those methods here. That's the histogram, like that's like the bar chart. It's not a histogram. It's a bar chart of how many of them have been discovered. We have discovered about 4,000 plus today. And then for the method, the most popular method is just transient. Transient is that if we have the observer on the Earth here, we have the sun, and we have the planet just goes through the sun. So when the planet just between the between the observer and its host star, then it will block the light of the star a bit. So we have the light curve, and the light curve has a dent, and the dent is caused by the planet. So as a result, we can use model fitting to know that what's like the size and the mass, and also like the orbital period of that planet. And we can know a lot because it just go from like the sun, so we can also see its absorption line. We can know that the composition, we can see like the size, we can just know a lot. And it has discovered a lot of exoplanet. And radial velocity is something that is like used the conservation of momentum and also the Doppler effects. So basically, the conservation of momentum just let us all like it travels around according to its center, but it's not the geometric center of the star, but the center of the planetary system, which is just a bit far away from the geometric center of the sun. And because this, you can see the sun just go forward and backward and forward and backward because of the influence of the planet, which would cause the red shift. So like red and the blue went back and the red went forward. This can help also use model fitting. You can determine the period and the mass of the planet, and it has discovered like about 20%, so it's also pretty much high. The next, we'll talk about the imaging. Imaging is just also sometimes it's called direct imaging. So just take a photo of the planet directly, but you need to block the sound. By blocking the sound, you can just put something in the camera and then block that. You can also send something, send like a shelter to the space and just try to block that. But it's not like send that to the sun, because send that to exactly the whole star because it's just so far away. Just stand up, try to find an angle that can block the planets, block the whole star's light, but the planet's light is not being blocked. And also, that planet cannot be so close to the whole star, because when you just like shelter them, they will be sheltered together. And also, like sometimes people use different wavelengths. For the optical wavelengths, the difference between the brightness of the whole star and the exoplanet can be just so large. But if we change to like radial wavelengths, it can be smaller. So you can take a picture of the exoplanet, and it has found 51 planets. So it's still okay. And astrometry is a method that I've only introduced, but it has only found one planet so far. But it's important because astrometry is a common astrophysics method, which also we have used in asteroid orbital determination that we have just briefly talked about. And astrometry is basically if if it's radial velocity, then the the star and planet plane is horizontal, but if it's um if it's astrometry, then the host star planet plane is vertical in your perspective. So you have several different stars around that star, and by just knowing about the location of the several different stars, also like at the same time because of the conservation of momentum, you can see the center mass. Like the planetary system go around the center mass instead of a geometric center of the star, so you can see the moving around like in all degree, not just like back and front. So you can take images and know about the exoplanet, but also like you can know a little about exoplanet, and it's just so hard to detect in this way because the surrounding star are also like move because of its own planetary system, and it's just so distant often that you can't even like see them. And the another method that we will talk about but more is the microlensing. So we have the graphs of microlensing stimulation here, and the left is the light curve, the middle is the stimulation, and the left is geometric structure. This is right. So like light curve, simulation of optical image and geometric structure. We can see that when the we have a planet pass like through the middle of the lens, it becomes so bright, and when the star just becomes so close to the lens, it also becomes so bright. So you can see the light curve. This is the light curve of planet, and this is overall a light curve of the whole star. So if we have this, then this, you can use model fitting to try to find the size of the information of the exoplanet, but you cannot know as many as the imaging because like imaging, you can know about the composition of the atmosphere, you can know its temperature, so on and so on, but you cannot do that like this. However, imaging means that the planet is just so close to us, but microlensing events is only message that we don't have to see the whole star to even find the exoplanet. The whole star can just be so far away from us that we have no idea where it is. So that's the only method that currently we can try to find the exoplanet beyond Milky Way, because beyond Milky Way we can't even see its whole star, and the planet is just so dim, so small, so indistinguishable. So we need microlensing events which can have high magnification rates, which means like dramatic effects. And then it's about theoretical foundation. So first we will talk about the physical theory of Microlensing events, then we will talk about cosmological distance, and then we will talk about superluminal motion. So the physical theory of Microlensing events basically is about geometry. So it has two approximation that is important. First is the weak field. So B, the impact distance. Impact distance is the shortest distance from the light and the shortest to the lens. So B, impact distance should be much smaller than the structural radius. Here, that's bigger is a mistake. If it's bigger, then like it will become like a black hole. The light will not like, go into the eye. And also single length approximation, it's just like when we do the optical problem, sometimes we consider the thickness of the mirror, the lens, sometimes we don't. And this time we don't because the distance between the observer, the lens, and also the source should be so distant. And then we can get the bending angle equals to this equation if it satisfies these two equations, these two conditions. And then, so that's like how can we get the Einstein angle, which is this angle. So like the angle between the main optical axis and the angle between the light that go into the observer's eye. And so as like this equation, how can we get it? Is just like because they're just so far away, like this, just so long. So this angle should be really, really small. As a result, we can just approximate. We know that when the angle is small, we can approximate sine like alpha or tangent alpha to alpha. So DLS times alpha equals to Fi, and also Einstein angle times DOS equals to SI. So we know the bounding angle and we could just derive this equation. It's not so hard. And also, in the most of the time, the source is not directly on the main optical axis, but to also do that, at that time, it will have two images. So this is again a simple geometric calculation, just ds a equals to bc, and dos, so like dos b ab, and then also dos Einstein angle, one of them ac, ab plus bc equals to ac, and then it's there. Yeah. If you haven't really learned this part, it's fine. You can just know that like sine alpha equals to tangent alpha equals to alpha with the angle is really small. So don't really worry about that, and just like if you like alpha like times this, it can just give you to like alpha times this gives you this. So like basically you can get a vague idea of like how this is like geometrically stands. Don't really worry about them. And is that the magnification rates or like the brightness of the like the effect of the like the source, the image of the source is proportional to the distance of the distance of the image to the length. So we can get like two of them because it's a quadratic equation. Quadratic equation gives us two solutions. We have two image, and so we will define U as the unit of the Einstein angle when the distance between the source and the lens is U. So the total magnification rate can be expressed like this, which is derived from here. And when the distance U is so small, we can get the A total. So the total magnification is approached to the infinity. And we can also calculate the crossing time. And then after we know all about this, what we can do is that we can draw a line curve of the Microlensing event. In this line curve, because like U and A is inversely proportional, so like when the U is really small, then we have a high magnification rate, and when the U, so U is like the distance, the smallest distance between the light and the lens. So if it's like large, then it will have a low magnification rate, and we can the crossing time we have like this equation can be calculated, so we can know more about the property of the extraplanar by model fitting. And then we'll talk about cosmological distance because the extraplanets, the stars are all in the universe. So Hubble's law tells us that the distance of the galaxy is proportional to the speed that the galaxy is moving away from us. So we can express the distance with the redshift. And so when we talk about redshift later, it just simply means distance. You can see that it's like pretty much the same. And so we have like the Hubble's law, which the velocity equals to the Hubble constant times the distance. So velocity is proportional to the distance, and this is according with the accelerating in expansion of the universe. And also we need to know the composition of the universe. Today's composition of the universe is not the same as the composition of the universe 13.7 billion years ago. At the time, we have like much more matter, but today we have much more dark energy because dark energy does not change its density when the space become larger. Universes become more spacious and more spacious today, but dark energy keep the same density all along. It's not like density become dilute ever, so it becomes so large. And so we are assuming that dark matter is matter, dark energy is not matter. So when we discuss about the problem, we will not really like distinguish. When we discuss about the composition of the universe, we will not distinguish dark matter and atoms. Atoms is just what we can see, what we can touch, all of them, but we will not separate dark matter and atoms because they are all matter. Dark energy is something that we have no idea. And dark energy is, as I say, that it definitely doesn't change and the space change, but the matter change. The matter, we know that if the density, if the space increase, then the density become lower. So that's like the difference between dark energy and dark matter. And actually, if our length can be planet and exoplanet, but our planet at our length, which the length creates a gravity, so like the gravity pull the light to make them bend. That gravity can also produced by the dark matter. And actually, we can use the Microlensing events to try to get to know more about the shape of dark matter, because we can know that whether the dark matter are clustered together, whether it's just so loosely floated everywhere. If it's clustered together, then probably our Microlensing events is produced by the dark matter. So we can just see the proportion of the Microlensing event and determine if the proportion is higher, much higher than we expected, then probably dark matter plays a role in it. Dark energy just doesn't produce a Microlensing event. It doesn't like produce a gravity as the matter does in that way. And then what we want to know the composition is that the space-time and the matter interact with each other. So the matter decides how space-time bends, and the space-time decides how matter moves. So this is according with Einstein's general relativity. So in general relativity, so the matter and the time, they can be equal. So matter equals time. This is just amazing. It means like matter and time are just the same. So that's why we need to get to know more about matter, to know about the distance and to know about the time. And then it's about cosmological distance. So universe is not equivalent. So since it's not equivalent, the distance of like all the above are not the same. We have luminal distance, conmoving distance, angular diameter distance, and so on. It's not the same. And here we use angular diameter distance, and you don't need to know about this equation. It's totally fine. But what we can get is that so angular diameter distance is not perpendicular. Oh no, it's not proportional with the redshift. So when the redshift is about 1.5, it has the largest value, and after 1.5, when the redshift increase, the angular diameter distance actually decreases. And we also don't really need to like use the function to describe this kind of line, but we can use a model in packages, the model that people have already provided us. So this graph I draw that with astropy.cosmology, a Python package, and it has a cosmological model in WMP5 and like WMP7, 9, and Planck 30 and 50. And why we have those is because we don't really know which one is true. It should be only one that is true, but the WAMP group has a larger value and the Planck has a smaller value, but all of them say that we get the exact true value, so we don't really know. And the flat just means that the matter and the energy, the sum of them equals to 1. So if you want to know the proportion of the energy, you can just subtract the proportion of the matter from the 1, and H naught is just the H naught is just the Hubble constant. And then because of this, we can just talk about how long it takes if we just use a normal source, the light. So if the source redshift equals to 1.69, the lens redshift equals to 0.85, then we can get the distance between the cosmological distance between the observer and the lens in the source with the following value. And we can get the Einstein radius, which is just related to Einstein angle. They have like a certain value to it, so don't really worry about that. So the typical value we can take is like 3.7 times 10 to the 14 meter, and we can just take the typical value of the relative velocity between the galaxies as 1,000 kilometers per second. So we can calculate this event, and what we get is that we calculate this event takes 15.2 years, which is just such a long time. And as a result, we know that events that is longer than 6 months cannot be detected because you will see different skies after it shifts. So we need to reduce that. What we can reduce that is that we can increase the speed. We can increase the speed of observer length or source if we want, but it's not really possible to improve the speed of the length and observe like relative speed between them, because the length is just the star and extraplanet that we want to discover. Observer is us on Earth, so we can only improve the speed of the source. So now we have an image. This image is the jet of the quasars. So the quasar first, like the jet of the quasar can move really fast themselves because they are just electrons, so they are really really light. We know that according to relativity, if something just approaches to the light speed, then it would be really really heavy. But electrons themselves are just so light, so even if it becomes heavy, it doesn't really matter. So it can travel really fast. However, on this picture, we have like 4 years intervals, and this jet of the quasar moves 27 light years, which we can see that everywhere it moves 6.75 times of the light speed per year. So it's just so faster, much faster than 1 light year per year, which means that it is doing superluminal motion. Superluminal motion is geometric, and we have the deduction here. So that's like AB, that's like the jet travel. It's travel at an angle to the observer. It's not travel like this. If travel like this, we will not have the superluminal motion. So that what it do is that this part, it takes longer time. This part takes shorter time, and because it's not travel like straight in this way, because this is a shorter time, so if we have like light fraction and all, it should be like faster than light because of the geometric effect. And this is a detection which, after I send the slide, you can look at it closely if you want. And then something, the condition of superluminal motion is that first the intrinsic velocity should approach to the light speed, which the jet of quasar can do this. This is evidence. This is just something that has been taken truly by the astrophysicists. And also the angle between the movement and direction of the site should be small. Then the discrepancy caused by the geometric effects should be like larger. And so here we can see that if we travel at about the angle between the movement direction and the side direction is about 8 degrees, and the jet is travel at 0.99 times of the light speed, then it can reach 7 times of the light speed superluminal motion, and it begins to do superluminal motion when it has like 0.8 of the light speed of the intrinsic speed. So that's a graph. You can see that how far it accelerates. So like accelerate that to like 3 times or like 2 times or 4 times is not like something that can be achieved. And the picture has shown it's 6.75, so we can also accelerate that really fast if we want. And then another is about time. So how long we will take now. So if it takes 7 times uh, light speed, superluminal motion, then we can reduce the event from 15.2 years to 2.65 days. So it's much, much shorter and it's observable. It's just between, it's within 6 months. And generally, probably it's not as fast like this, but we can reduce that to about 10 days. So it's great. And then we will talk about Microlensing light curve of planetary system briefly, and the detection rate of planetary system, and the machine learning auto classification of Microlensing events. So it has 5 types of the light curve. The first is resonant channel. So the orbital semi-major axis approximately equal to Einstein radius. So just like this graph. So like this has like it's like about the same. And this is the commonly model for the Microlensing events that has happened in the Milky Way. It has not a high magnification, only 3, so it's like relatively small. And for 2, 3, and 5, 2, 3, and 4, they are like the light curves that we cannot really use them to model to a certain or like a unique type of planet and star system. So they're not really useful. They all have like orbital semi-axis, which is larger than the Einstein radius. So they're separate, and we can sometimes people cannot discover that because it take a gap. And for this is just not giving much detail. We don't know what it is. We don't even know if it's a planet or if it's whole star, so it's confusing. And this is also confusing whether it's star or planet. It just has so many conditions that can be fit to this graph, so we cannot determine that. And this is called white channel. So it has like some like not symmetric shape here, and it has a high magnification rate, but that's also not the situation for the exoplanet and planetary system in the beyond Milky Way. So what we have is this white channel, one center channel. So the optical semi-major axis should be much smaller than the Einstein ring. Einstein radius. And here we have the asymmetry, and the symmetry is just caused by the planet, and we have high magnification rate, which means the impact distance is really small. And in this way, we can model fit to find the mass and the orbital period of the exoplanet. We can discover the exoplanet in this way. And then we will talk about the detection rate of planetary systems in the universe. So what we can do is that we can assume that it's at a large scale. At a large scale, galaxies are distributed uniformly and are the same in all directions. Here's the picture. You can see it's like generally distributed uniformly, but on a small scale that is clustered as galaxies. And what we can assume is that the planetary systems are evenly distributed in the universe. The mass of the stars are all the mass of the sun. We ignore the mass of the planet because the mass of the planet is much, much smaller than the mass of the stars. Although like this is a rough estimation, it is enough for us. And also like because the volume density of the planetary system in the universe is changing, the planetary system obviously they are like made of matter of the parts that we know about. So we need a co-moving volume, the volume in which the number densities of non-evolving objects flow into the Hubble flow are constant with redshift. Don't really need to understand that, but we are just using co-moving distance. And we can guess, we know about like the current star mass is about 5% of the critical density of the universe, which means that if we have 1 square meter, 1 meter 1 meter solid, and you will have only 5 atoms in it. So it's really small. And because the light curve of type 5 has high magnification rate, the impact distance B is really small. So it's small means that the light should be really, really close to the length in the Einstein ring. So like Einstein ring can be like all array, but we only need this small part of it. So we only take 1% of like whole area of Einstein ring, so F equals 1, and we integrate it to the cosmological distance, and that's what we get. And according to this graph, when the redshift is larger, more Microlensing events could be observed. So if the universe is distributed evenly, then the chance of detecting a Microlensing events is 1/10 million. However, that's like so hard to detect. But on average, a galaxy has 10 billion stars, and we can searching for the target galaxies. And target galaxies means that we will have like the background source, quasar, and also the spectrum of the quasar has the absorption line, which means that there's galaxies before that source quasar, and then we can increase the probability by 10,000, which the probability of detecting a Microlensing events is 1/1000. So 1/1000 means that it's much possible to do that. And also because of superluminal motion, we actually accelerate the speed of the source scans through the same volume of the universe. The probability of detecting Microlensing events per unit of time is increased a lot from 10 from like 1000 kilometers per second to several times of the light speed. And also, finally, we'll talk about machine learning and auto classification. So machine learning, mostly astrophysics, is just classify which type of star, which type of events, which type of deflects. So classification. And also, like, why do we need auto classification? Because the um, like the vary in light, the magnitude probably is not caused by Microlensing event, but it can also caused by binary. So binary just like go around each other. They can have light change, and also the light change can be caused by vary stars, which includes different types. And the characteristic of Microlensing events is that it's symmetry. So if it's symmetry, then the vary star possibly don't have that. Also, it's periodical. So the binary star is it's not periodical. The binary stars are usually periodical. So with this characteristic and with a lot of new data trends in the data sets, we can use that to also classify the Microlensing events. And when as classify Microlensing events within the Milky Way, we have the algorithm called length identification algorithm. However, what's more is that we can like modify this to detect the exoplanet beyond Milky Way. That's like Microlensing event, vary star, and several like that's the different shape of them. They have different characteristics, so their machine can help us determine if we train them. So detecting exoplanet deep space is practical with superluminal motion because like we can use the superluminal motion of the source to reduce the time of Microlensing events to about 10 days, when the probability of detecting exoplanet system could reach about 1/1000. So when monitoring remaining quasars in the galaxies in front of it, we can use big data and machine learning to auto recognize the Microlensing events. We can do the following up observation after we recognize that with like several telescopes, like all telescopes that can go observe. And also most observations are done remotely today. And then we can find dozens of planetary systems in a year. So that's this part, and also feel free to ask questions. Now we don't have a lot of time, so just ask questions in the chat box, and I will just go through to the next part. And you can also like discuss with each other in the chat box if you want. Also, like I will like try to I think I will try to like when I share the document, I will share like put an empty slide in like probably the Google slide that you can like write questions there. They can try to answer them, and also you can try to have like discussion there if you want. So yeah, I shall I like share. You can see the PowerPoint, right? So this part is about postmodernism literature. Why I talk about postmodernism often because postmodernism has a lot to from like the scientific ideas, from the relativity, from the uncertainty, the Copenhagen uncertainty, and also it has like a lot to do with like machine learning or just the era of big data, the era of internet. They have all caused postmodernism, and postmodernism is just like the characteristic today. So you'll see like a lot of idea what you are familiar with. So what is postmodernism is like incredulity toward narrative because like relativity says that's not like absolute truth. And also uncertainty tells you that you cannot like, know about everything at the same time. And quantum mechanics tells that like everything like a color of this bottle can be like any color at all. It can be like right around to both sides. It can be both colors, so it's hard to believe. And it's like a product like progress of science. So so like we have like the meta narrative. It has like dispersed in the cloud of narrative language in elements such as narrative, but also the narrative, prescriptive and descriptive. Also like on a biological um, scientific side is that people just lose their memory all the time, and a lot of like psychological effects or physical effects can change their perception of the world and change their memory. So we don't know if the person remembers well when the person tells those things. So postmodernism is a conscious problematization of what is true and real, and an inquiry into how truth and reality are made rather than found. So the precursor is Kant's Copernican revolution. That is his assumption that we cannot know things in themselves, and that objects of knowledge must conform to our faculties of representation, and certainly must be meditated through a theater lens, and which removes the immediacy towards the things that is now. And also like living now is like a more recent, like more postmodernism idea. Like in the past, people like live for future, but now people live in now because we don't know the future. It can be so fragmented. It cannot be true. And this is like a like quite like ironic comic, which like that person stand on the neck, but this person says that it's not like I stand on the neck. It's like you hit my feet with your neck. It's like perception. And then it's about like understand the postmodernism versus modernism. This attitude toward perception and subjectivity, as objectivity and knowability, fragmentation, disorder, and towards belief system, alienation, outside status, and otherness. Also, like the global and the local things can be both fine. It can be really meticulous, or it can be so detailed, which we are talking about maximalism and minimalism, which are like the characteristic of postmodernism. Maximalism just describe the person all in detail. Like you can describe my face like in like 30 minutes, but also like you can say that I'm not my person. I'm only I just walk on the streets, which is so reduced. So it can be both maximalism and minimalism. And so the perception and subjectivity for postmodernism, there's no reality, only construct or stimulation. So probably like we live in the simulation of a virtual world of a really accurate programming, and we don't know if our world is real or not. And modernism just emphasized how seeing take place. It's a lot about consciousness. And modernism is movement away from omniscience and fixed point of view, clean cut of moral and aesthetic positions. But postmodernism is not. In postmodernism, they think that everything is subjective, just like relativity. So no position is essentially true or better than any other. And incredulity, which I've mentioned before. Modernism thinks that fragmentation is something tragic to be mourned about, and works of art struggle to preserve some coherence. Postmodernism is not just we jump around to talk about all the things, and postmodernism is just about like we are as a lot of organization, we have a lot of platform, a lot of social medias. Like you can become different yourself. You feel like you are fragmented into pieces, and it can blow your mind up, but you don't really think it's about the things. And still, you are trying to bricolaging, and bricolaging is recognized as art, a piece of art. You're trying to bricolaging, but bricolaging doesn't mean coherence and doesn't mean that being fragmented is not good. Probably it's reflective. Probably fragmentation let you rebuild yourself. Fragmentation let you try out different role which can promote the equality or so on and so on. And for the modernism, it seems that the face tends into doubt and despair, things fall apart, the center cannot hold. Failure of master narrative causes despair and cyclism. However, postmodernism, like if you fail to narrator, like you are like failed narrator on something, probably it's just a way that you are discovering yourself, or like you're just trying to break down the traditional framework of the world and bring innovations and creations. The narrative can be really invalid because like also the boundary line between the machine and the human are just so close, and you know that if it's like it doesn't need to like everything has a exact frame formula. We can substitute new ones for the old and stop worrying about it. Postmodernism, modernism thinks that others outside the mainstream, look at the mainstream society, it's quite like it's not, it's like a little bit exclusive, and the tensions between learning to belong and rebellion. But postmodernism, you can be an outsider. Being an outsider probably means that you are master, you are so unique, you are being yourself, you are not just so influenced by the mass culture, mass products that probably people deem are probably like not so characteristic, but you are going to make your difference by not sticking to mainstream. So some ideas that influence this, including post-colonial idea, regional idea, and gender-based studies. So yeah, so like you don't need to be in the mainstream. You don't if you are minority, also be respected. You don't like try hard to become the majority. That's not something. It's like postmodernism think like it's good, and modernism is like it emphasizes national institutions, commodities, values, and beliefs, and it thinks that urban manufacturers, postmodern, post-romantic things are great, but like postmodernism, it can be multinational, multi-ethnic, it can be marketing, consumerism, it can be culture capital. Culture is uh, culture is the wealth, background difference are all the wealth. Uh, like it can be all local or like urban, but it's a local view. People will go and appreciate its uniqueness, its serenity, and because like we're just all so close, the world is pre-collagen together. It's multinational, and so there's like precursors. So like before it's like conformity, compliance, and like knowing each other, but now it's like people want to like distance themselves from mass consumption, distance themselves from material success and the distribution of power in society. They want to break that frame and create a new. Modernism attempts to reveal the profound truths of experience in life. However, postmodernism would just let you yourself to guess, and it doesn't have something that's profound. Everything is just down to earth, and it's so planned, and it focuses on like your reaction to different texts can be really different. You can choose to make the answer by yourself, and the author and the audience are interactive with each other, and author and the narrator in the book, they can also like talk. So you are like actively engaging instead of just percepting the ideas passively. And modernism, it focuses on the central themes and a united vision in particular piece of literature. Most authors guide and control the reader's response to the work. Postmodernism has open interpretation, it's not guided, and postmodernism itself is really important. Postmodernism sees themselves as ambiguous, contradictory, inconclusive, fragmented, and jagged. So a person like the book which I will introduce, like here, I don't know, like City of Glass. So City of Glass, like the person, uh, he is at the same time Paul Auster, Max Work, William Wilson, and the person is also Daniel Quinn. So the person is really jacked, and the person is just exploring their identities. And so for postmodernism, largely a reaction to the assumed certainty of scientific or objective efforts to explain the reality, it stems from a recognition that reality is not simply mirrored in human understanding of it, but rather it is constructed as the mind tries to understand its own particular or personal reality. Also, like, it can be really skeptical about the explanation of the group's cultural traditions and races. Um, like, people can have their own interpretation. It doesn't have to be construed by the mainstream. And everything is about interpretation. Everything is about a lot is about individuality, a lot about subjectiveness, and also so like postmodernism, it just came from like those person's skepticism, and also it comes from like so like for them, like no theory can be ever proved to be true. We can only show a theory is false by proper. Also like Gödel's, no theory can ever explain all things constantly. And probably that's why people cannot find the unification law. We don't know that. And there's always a separation between our mind and ideas of things and the thing itself. That's why it counts. And also the Copenhagen interpretation, Heisenberg uncertainty, and also like science concept and mental constructs. That's like the idea about logical positivism. And metaphysics is empty of content that has also like influenced postmodernism, and also as a result, the absolute and certain truths expand all things is unattainable by postmodernism. Some elements of postmodernism, including irony, absurdity, playfulness, and black humor. So people just treating serious subjects as a joke. This is kind of similar to like Mark Twain, some of like Mark Twain's work, or like a poem of a person, which is the poem is called Statesman, or uh, like Jonathan Swift's book, like Jonathan Swift, like it's so like postmodernism is blending of styles. So you can find some similarity between the work of postmodernism to the work in the past. I really find like Jonathan Swift is like the person really have like this style in the past, not in this century. And then it has a distrust of theories and ideologies of author and narrator, undermining his control of one voice, of the modern assumption about culture, identity, and history. Also, it has pastiche. So pastiche means mixing genres as paying a homage or a parody of the past literary styles. So yeah, past styles, it's like a mixture. Some people argue that postmodernism is not really a style because it's not something that's unique. And then metafiction, the metafiction is just the artificiality of the writing is just shown to the reader. So like in the City of Glass, they have like the real Paul Auster, the author, and the Paul Auster narrator, and the Paul Auster author in the book is painting the Paul Auster as a narrator or the Daniel Queen of the narrator that Daniel Queen or poster in the book is just fake. The poster in the why do people like say that Poster can save the whole things because Poster is a writer. The writer can write the end whatever he like. So it's like hinting about this is not true. This is story. The author has a control, and the audience also has a control, but it's fake. And then it's about techno culture and hyperreality, like because we have like a lot of AI, deep learning, machine learning, all the things. We have a lot of technology that which has like bombard us by advertising. We have like self promotion on our channels, and we have ambiguity about like what's a real. Like I live in my city, but I can get information from all over the world. So it's like sometimes confusing, like where exactly you live in. Maximalism and minimalism I have talked about before. So much detail, so much reduced. Both characteristics of postmodernism and historiographic metafiction. So fictionalizing the actual events and figures from history. Fiction is about just blending different ideas of different parties, different facts and fictions. Temporal distribution is that the events can overlap and repeat, and the time which just passed like 2 hours, they can feel that it's 15 hours. The time like inside a house and outside of a house can be completely different. That's temporal distortion. Some like time may be like appear just so unbelievably long or unbelievably short. And magical realism is that all dreamlike. You can describe about dream. It's about like surreal and bizarre and myths and imagination. In the textuality is people just mention a lot of different texts like instead of glass they mention about like the Tower of Bible, and it's mentioned about the like a music piece by Haydn, and it mentions like it mentions like Henry Thoreau. It mentions about like a lot of ancient philosophies, and it mentions Alice in the Wonderland. It just mentions about lots of different things, and it uses the elements of a lot of different things, and also like allusion of a lot of different texts with intertextuality in postmodernism. So like intertextuality feeds like some big question about literature. Can text be seen in isolation, or do we need to look at how it relates to other texts? It does not disguise that it's just a literature, so that it's like it can like refers to other literature to make it like more fake. And hyperreality, so because like we have television, multiplayer online game, virtual reality. We have AI, deep learning, which deep learning and machine learning which belongs to AI. So the world is just not really certain about what it is. Flattening of effects is just about human become machine and machine become a human. Like an example is this 2001 F Space Odyssey. So the person like actually become like a commuter, and commuter how become a person like that. And the potential problem of postmodernism is crushing sense that there's nothing new to create. A focus on dystopian narratives without suggested and avenues for avoiding dystopia, and also stylistic masks without content. The meaning can be a mimicry. So that's like basically what about postmodernism, and characterized by irony. It's like self-reflective and a lot of allusions that can be really absurd sometimes. And set of gloss, that's books that are recommended to read and a representation of postmodernism. So my time is up, and I have also like finished my lesson exactly. So thank you everyone. Thank you, and you can ask questions like when I like post a slide on the I think on the web page of our class. I will like put some blank slide, and you can put your question there. And you can also have a discussion there if you have anything that you haven't like asked and discussed yet. And also, fear you need to like fear this survey before leaving the Zoom. So thank you, everyone. Thank you. The survey has been sent in the chat. Thank you for participating. It's really nice to see you here, and it's really nice to be here to have this opportunity to talk about them.